So in the last two videos, we saw some pretty amazing stuff. We had a type comment that referred to itself, and then we had a function that called itself. And that function actually did what we wanted it to do, instead of just going around and around in circles on and on and on forever. Now, why is that? That's what I'm going to talk about in this video. There's some pretty deep computer science underlying all of this, and we're not going to get into it in kind of more academic terms. But what we will see is that the type comment has two key properties. And the way we derive the template preserves those properties so that we end up with functions that work properly even though they call themselves. So what I'm going to do is explain that, make a few additions to the design recipes so that you can keep doing that systematically and producing recursive functions that work properly on your own. This file is Quidditch Recap Starter. It's basically just the solutions from the last two videos rearranged slightly so that I have both parts of the problem in one box. That gives me some more room below. The first thing I want to note is right here in the problem description. Notice that we're designing a program that will keep track of your favorite Quidditch teams. Now ask yourself, how many teams are there? We don't know ahead of time. There could be 1, there could be 2, there could be 30, there could be 60. We just don't know ahead of time. This is what we call arbitrary sized. Arbitrary doesn't mean random, it just means we don't know ahead of time. Now, whenever we have an arbitrary sized data problem, whenever we need data to be of arbitrary size, what we're going to see is that we want to use self-reference in the type comment. This type comment has the self-reference in it, as we noted before. And we saw how that made it possible for it to account for lists of any size. We just make one more cycle around the self-reference relationship for each element of the list. But why does this self-reference work out? Why doesn't it in some sense blow up because it just keeps going around? Well, the key thing is this is what's called a well-formed self-referential data definition. And it's well-formed because it has the self-reference case, that's true. That's what lets it get longer and longer. But it also has the non-self-referential case, or the base case, and that's what lets it stop. So in a well-formed self-referential data definition, you always have both a base case that has no self-reference and a self-reference case. Now this is a simple self-referential data definition. It's possible for these type comments to have more than one self-reference case and more than one base case. The rule for being well-formed is that there has to be at least one base case, non-self-referential case, and at least one self-referential case. So the summary so far is, if you have an arbitrary amount of information you need to represent, you need to use a well-formed self-referential data definition. That gets us to here. And if we look at the How to Design Data page, what we've got so far is reflected here in the choice of what form of data definition to use. When the information to be represented is of arbitrary size, we use a self-referential data definition. Mutually referential is something we'll talk about in another week. So if we follow this link, it says that we need to use, for arbitrary size information, we need to use a well-formed self-referential data definition. So that's how the How to Design Data recipe accounts for what we've seen in the code so far. Let's go back to the code now, and let's talk quickly about the examples. For self-referential data definitions, it's good to have examples of the base case. If there's more than one base case, then have examples of both base cases. They tend to be kind of trivial, but I like to put them in anyways. And you should have examples of the self-referential case. In this particular data definition, I probably could have done with just 2 examples rather than 3. So I probably could have done with example 1 and example 3. It's fine to have an additional one. Now let me scroll a bit and talk about the template. As we saw before, the beginning of the template is relatively straightforward. It's one of with 2 cases, so that got us the cond. The first case is atomic distinct empty, so that got us cond empty question mark LOS and ... This case, the second case is cond, so that's compound. we take the cons apart into its first and its rest. But then the question is, how did we get this fund for LOS? Well, the reason we got that fund for LOS, let me just back up a little bit to where we were right at that point in time. We knew that first LOS was going to be a string, and we knew that rest LOS was list of string. So we're not going to do anything with first LOS because it's primitive type. String is a primitive type. But with rest LOS, here's where we're getting the self-reference. There's a self-reference here back to list of string. When we take the rest of LOS, we're holding a value of type list of string. And so there's a special template rule called the self-reference rule. And we use it in this case, and the self-reference rule says wrap that selector in a call to the template function itself. And this thing is what's called a natural recursion. It's a recursion that shows up exactly where in the type comment we have a self-reference. So what we have so far is arbitrary size data, well-formed self-referential data definition, have examples of the base case and the self-reference case, and in the template, when you hit the self-reference, put in a natural recursion. That last bit shows up in the data-driven templates page right here, where it says if you have a self-reference, form a natural recursion with a call to this type's template function. And that's what we did here. We put a call to this type's template function because we had a self-reference there. And that's why this call, this natural recursion, corresponds exactly to this self-reference. And I've tried to draw the arrows here to show that correspondence clearly. So from now on, whenever you see a self-reference in a type comment, you'll immediately know that there's going to be a natural recursion in the template. Now let's look at the function we designed. So the signature is pretty straightforward. Nothing really new here except that it does consume list of string. The purpose, similarly, we knew how to do, and the stub. And the check expects look pretty familiar, but there are a couple things I want to note here about check expects for functions operating on lists. First, remember that check expects are always examples first and tests later. So we use them as examples to help us figure out what we're doing. And with that in mind, it's always a good idea to have the base case example first, the base case test first. That's what I have here. I have contains UBC of empty as my first test. Partly that helps us figure out the simplest case first, and also many tests of these functions end up at the base case, and so if the base case result is wrong, that can affect other tests. So it's good to get the base case debugged first. So there's two reasons to put the base case first. One, it helps us figure out the simplest thing first, and the other, it makes sure when we run the tests that the base case works properly before we test the other cases. And another general guideline for functions operating on lists is to be sure that you have a test that operates on a list that's at least 2 elements long. That's because sometimes there's certain kinds of bugs you can introduce that don't show up in 1-element lists. This particular example is also an example of a function that has 2 different cases in it. There's cases where it finds the string it's looking for and cases where it doesn't. And so in that case, of course, you have to be able to test the true and false case. Finally, let's look at the function itself. And to look at the function, what I want to do is I'm going to back up. So what I'm going to do is I'm going to delete this and go back to the point where we just had the template. When you copy the template down for a template based on a type with self-reference, then the template has a natural recursion in it. And it's very important when you rename the function that you rename both the function definition and any natural recursions. That's very important, and we'll see why in a minute. So now let me start coding the details. Let's see if the function is operating on a list that's empty, then we can't find UBC in an empty list, so that would be false. Otherwise, these examples tell me that there's 2 different cases depending on the first item in the list, If the first item is UBC, we produce true. If it's not, we need to go look farther down in the list. So that makes me put an if in here, and I say string equal question mark UBC. If the first item in the list is UBC, we're going to produce true. And otherwise, what do we need to do? Well, the first item in the list might not be UBC, but there might be a UBC farther down in the list. So we need to go look farther down in the list. And the key point here is that we want to get you to trust the natural recursion. At this point in time, you need to know, is UBC in the rest of the list? And because the template has included a natural recursion, and because that natural recursion came from a type with well-formed self-reference, you can count on the natural recursion to work. So we're just going to trust that contains UBC of rest LOS does what we need it to do. And the key thing is I want you to avoid the temptation to edit in here. Trust the natural recursion. That's the game. And the reason you could trust it, again, is because it came from a well-formed self-referential type. Let's see. All 4 tests pass. What I'd like you to do now is go look at the How to Design Functions and How to Design Data and Data-Driven Templates web pages, and pay attention to the parts that talk specifically about designing with lists. Just go ahead and review that, and then you'll be in a good position to keep designing with lists going forward. And remember, the big summary of kind of what we've seen so far is, if you have arbitrary size information, then you need arbitrary size data. That requires a well-formed self-referential type comment. That leads to a natural recursion in the template. That leads to a recursive call in the function. You should test the base case first, and you should always trust the natural recursion.